Our next speaker, who's sitting right next to me, is Marcelle Soares-Santos. She's going to tell us about the science breakthrough of the year. And of course, you play a central role in that, and it's a pleasure having you here. Thank you.
Thank you. Thank you. Okay, it's my pleasure to be here today and talk about this result that is spectacular, and it's going to be celebrated in a great fashion as well tomorrow on the plenary talks, right? I need, perfect. Okay, so let me start by answering a question that comes up very often when I start talking about this science to people who happen to not be paying much attention or not be experts in the field. The question I often get is, well, but didn't those guys already get the Nobel Prize? Why is this still interesting? Isn't it a story, an old story already? And I'm trying to show this slide here to try to address that particular question. The story, at least in my view, one of the most exciting things about that result was the fact that there was more to come, was the fact that we could expect, realistically, to have not onesies and twosies, but large samples of gravitational wave detected mergers so that we could study them. And in particular, those mergers that would involve at least one neutron star in it would have material that would be bright enough that we could observe with what are now called conventional astronomical techniques. And the combination in that case of these multi-messenger investigation is something that would have a great payoff. And that is what have motivated quite a few people in this new field. In particular, here I'm showing a list that is not complete. It's just a selection of some of the topics that can be addressed by combining gravitational wave and electromagnetic information from the same objects. So if you're interested in astrophysics, if you're interested in learning about the origin of the R process elements in the universe, or the history of formation of binary or multiple systems with 3 objects, and there is something for you in this field. Or if you are interested in cosmology, which happens to be my favorite topic, there is something for you there as well. As I'm going to show briefly, we can use these systems to measure the rate of expansion of the universe in a beautiful way. Or if you're interested in other more fundamental physics studies of the nature, for example, a time-of-flight experiment of comparing the time of arrival of these different messengers, there's something for you there as well. So each of these topics is not to be seen only as a potential thesis topic, but probably potential careers to be developed in the pursuit of understanding those things. And the ones, in a few of those have been already touched by this one event that was discovered. So that's the reason why it's so spectacular. It's the first neutron-star merger that we have detected, and it already delivered a lot on its promises. So what are the expected signatures of a neutron-star merger from the point of view of, again, the traditional astronomy? There are multiple signatures, and this is again another way that these systems are really beautiful and interesting. So here I'm showing two versions here of what you could see from a merger, and one of them is coming from relativistic outflows. So that is, for example, jet, then in the direction of the pole that is represented there beautifully in this artistic representation or simulation. And the other one is relativistic outflows. So that is material, that is the region of material that would be, for example, powered by our process, nucleosynthesis, that will heat up this material that is being ejected from the system. What it characterizes these two different mechanisms of emission is the time scale of their evolution, that they evolve, and also the wavelength that they emit. So in this case, it means, in the case of the jet, we are talking about gamma ray, X-ray, radio emission, while on the case of the R process powered emission, we are looking for emission in optical, infrared, and a little bit on the UV. And what is great about that, if you're an astronomer, is that this caters to astronomers of every flavor on every wavelength possible. So this means that these detections are going, you could expect that they are going to engage a large fraction of the astronomical community and a large fraction of physicists, and will require development of new ties between these communities that sometimes are not very used to work together. But as I will show, we are learning fast. We are learning quite quickly. Okay, so I hope that I motivated you that pursuing the challenge of finding the EM or electromagnetic signatures corresponding to the gravitational wave events that LIGO and Virgo can see, that is something that's worthwhile. It's worthwhile our time and our effort. Now let's try to make an assessment of how big a challenge that actually is. This plot here, which was made by collaborators of mine, shows on the y-axis the area, sky area, and in the x-axis is the fraction of the localization probability enclosed by that area. So if you look at maybe 90% confidence level probability there, you will see on the left that you need to cover a large area of the sky, something almost like, I have some numbers here to help you, 500 square degrees. And that is the case when we would have only 2 gravitational wave detectors operating, for example, the 2 LIGO detectors. On the other side, on the y-axis, is again area, but the scale is about 1 order of magnitude smaller. And that is because when you add a 3rd detector, your ability to triangulate the signal goes up significantly. So for this reason, everybody was extremely excited last year when Virgo joined LIGO in observing jointly the sky. And this meant a significant shrinkage on the sky area that we had to cover. Now, about 55 or 60 square degrees, which is the median area for achieving something like 90% confidence level for a given typical event, it's still challenging. It's not easy to achieve that. And in particular, if the objects are faint, it would be difficult. But, and here I'll jump to make how can I say, acknowledge that this effort, as I said earlier, it involves people with expertise from different corners of the astronomical community, and involves our colleagues on the gravitational wave community, and it's a beautiful large effort that involves literally thousands of people, hundreds of institutions, and all driven by the motivation to do this science. I don't expect you guys to read all of that, but it's just showing the number of people that signed off on the joint paper that was published and with the announcement of GW170817. Now, so what happened? What was the process? What was the achievement that we are here discussing today, and that we are so happy about? So this merger was a merger of 2 neutron stars that was detected in the gravitational wave detectors, and 2 seconds later appeared in a gamma ray burst. That alone would have been already spectacular, okay? And that was just the beginning of the story. And in addition to that, as you saw in the title slide, I had an example of an image in the optical wavelengths. We were able to identify the counterpart and pinpoint what it is. And I'll tell you the story of how we got there step by step and walk you through how we achieved this. Okay, so the story starts on August 17, 2017, early in the morning for those who are in this time zone. And the object was at a distance of 40 megaparsec, which is about halfway through the distance that the detectors were sensitive to in that last run. And it was a binary neutron-star merger, the first of its kind. So this event, for these 3 reasons, made everybody that was involved in this, like a large fraction of those 1,000 people, drop everything else they were doing and engage in pursuing the follow-up observations and trying to understand these systems. I think that everybody who was involved in there will remember forever where they were on August 17 of last year, because it was really a memorable day. So as I mentioned earlier, the multi-messenger aspect of this discovery was settled by, was established by the fact that gamma ray burst was identified merely 2 seconds, so in coincidence with the gravitational wave signal. So that per se is the moment of inauguration of multi-messenger astronomy with gravitational waves, not counting with neutrinos, which we've been doing for so many years already with the sun. But this is really an achievement and a landmark achievement that these 2 communities were able to do together. And again, if we had stopped here and nothing else had happened, it would already be something to celebrate. Now, but there's more, right? A lot more happened. And so the next question is, well, where's the source? Can we pinpoint what it is? So the sky map that you're seeing here shows a combination of the localization regions as indicated by LIGO alone in light green, LIGO and Virgo in brighter green, and the blue contours show the localization areas that were inferred from the gamma ray burst, the gamma ray satellite data. And as you can see overall, 2 things are remarkable. One of them is that in this map, the gravitational wave data is actually the portion that provides the most stringent localization area in the sky. And so the new messenger arrived with a huge impact in this already. And in addition to that, you see that the localization area is in this case here, it's about 30 square degrees. So it's of the order of magnitude of what we were expecting for an event that has the 3 components, even a little bit smaller than the median event. So that's good. It's good news for us. And on the smaller red contours over there, what you can see is the region, the LIGO and Virgo region, and highlighted, the little dots highlighted are the brightest galaxies in that volume. And as you can see, there are quite a few, but it's not an overwhelming many galaxies. And this was a key factor in the strategy that some of the groups utilized to pursue and discover the optical counterpart. So let's go to that stage of, okay, now we want to find the source. What you have are these sky maps and a list of galaxies perhaps that are the brightest galaxies, where you imagine that the probability is high that the event came from there because there's more mass there. So what do you do? Well, I should add that the challenge in this particular case for this event was not only to search the entire area, but to do that in about 1.5 hours of observing time. That was about the amount of time that we had before the region would set in the sky. What you're seeing there is a map of the sky showing a snapshot of the region that you could see from Chile. And the regions, the contours are again the 50 and 90% probability contours, and the red corresponds to the tiling schema that our team chose to map out the region. What you notice is that the horizon is very close to the region. So within 1.5 hours, this sky will have shifted enough that you will no longer be able to reach that region. And that will be a problem, and that means we have to act fast. Another thing that was peculiar about this event it was that because it was so close and the number of galaxies in the region was manageable, the attempt, it made sense to have people looking by eye at some of those images, eyeballing them, in order to identify quickly, even faster than we could with our software. So in this case, I'm describing this because for us, in particular, for me, when I was preparing for this, I was expecting that we would have much larger areas to search and events that would be further away. So the idea would be, now it makes no sense to go galaxy by galaxy. It makes sense to scan the entire region and use an automated software to do it. And that is still a strategy that we used for this case, and it's the strategy that we think will be useful once we start seeing more events that are further away. But this case was special. We had this event being so close that it was worthwhile sitting there and having a team of people eyeballing the images as they come. And that strategy was used not only by us, other groups used the same strategy. So at the end, this effort paid off handsomely, I should say. And we were one of the groups that identified the counterpart that you can see highlighted there by the tiny white crosshairs. And it was really a spectacular moment. But we were not the first ones to see that. Another team, the SWOPE team, of which our esteemed chair is a member, they saw it first. And so this is the image, the discovery image that the SWOPE team put out. And what is really interesting to remark here is that this is a small telescope in comparison to the telescope that we are using with a narrow field of view. So for them, the only possible strategy was the galaxy by galaxy strategy. And they executed that to perfection and were able to be the first ones to announce the discovery, the detection of this source. And so from this point of view, one lesson to learn, I think, is that in this emerging field, I think there is room for a variety of creative ways of using the diversity of resources that we have available. And at the same time that things will become more and more challenging as events will become more distant and perhaps more faint, I think there is still a drive to try to utilize in a clever way the resources that we have. It was not only SWOPE and the Dark Energy Survey team that saw this event first. There were in fact 6 teams that independently discovered this source. So I'm listing here all of these papers. And so this was really spectacular. So within 12 hours from the merger happening, we could pinpoint in the sky where it was. We had information on several wavelengths, and we were already prepared to do detailed follow-up observations to understand the evolution of this system in all of the wavelengths. So that is, I think, one of the the great things that was enabled by this rapid discovery of the counterpart. Now, obviously, the question is, okay, probably wouldn't have been the same if the source would be at, for example, 100 megaparsec or so, which is the typical distance we are expecting for future events. In that case, if we are really looking at sources that are further out, we really need to invest in cross-checking and vetting, making sure that the candidates that we find are the actual counterparts and not something else, some other transient masquerading as the counterpart. And in order to do that exercise with this event, what we did was we revisited the entire area again after the source had already faded. And we did the analysis as if we didn't know the source was there. So forget that we know the source is there. Let's do the analysis applying certain criteria to select out junk detection or a background detection like supernova, for example, and try to see if we can recover the source. And the answer is yes. Out of 1,500 candidates that were present in this entire area, after we apply our selection, there's only one candidate remaining, and it's the candidate that we know is the right source. So this, I think, bodes well for the future because we can use this technique and use simulations to estimate how far we could see the source. And the answer is out to about 400 megaparsec, which is great news because it's way beyond the limit out to which we expect these events to come in the next few years. So I think we are in good shape to see more of these events when they come, and they will. Now, we identified the source. What's next, right? So in the next few minutes, what I'm going to do is go over in a very condensed way, go over some of the amazing science that we were able to do with this event. So number one thing that we want to do is to watch it evolve in all possible wavelengths so that we can see, study its evolution and see if the prediction of the emission that we had before, the model that we had about these R process, nucleosynthesis powered shell of material expanding, etc., if that still holds or not. And what you're looking at here is the light curves obtained. It's a compilation including the data that we took with our camera and data that was taken by many, many other groups in all wavelengths from UV to infrared. And what you can see here is that overall, the shape of these light curves corresponds to what we would expect from those models in general. In detail, there's a wrinkle, and there's always, as usual, when you go from the theory to the world of reality, things are a little bit more complicated. So as it turns out, and I hope this video will work, yes. As it turns out, this system is at least the best fit for the data we obtained for this is a system where we actually seem to have two components. Both of them are processed nucleosynthesis material, but in one case heavier material, in the other case lighter material, so lanthanide richer in the case of the red component. And that means that one of them has a higher opacity than the other and expands at a lower rate. And this means that is the reason why the evolution of the blue components of the light curve is much faster, it decays much faster in blue than in the red colors. This is the new model that we are working with right now, is that it looks like the kilonova model, that is the name we are giving to these new class of transients we discovered. The kilonova models are a little bit more complicated than we thought, at least in the case of this system. We are really looking forward to have more systems to actually check out if this still holds. But this, I think it's already something new, and we added a new component here of understanding of this new transient. And it's interesting to see as well that oftentimes in astronomy, it takes years between discovering a new source and understanding the workings of it. In this case, we made progress rather quickly. Now, what about the other wavelengths? I talked about the UV optical infrared. What about X-ray emission? As it turns out, the X-ray emission was a little bit delayed in activating, or so to say. It took about a week. And another thing that was interesting as well was that this emission continued to brighten while the optical near-IR component was dimming and disappeared. The X-ray emission was brightening for months after the source was identified. And the explanation for this behavior is consistent with GRB afterglow when you're observing it from an angle. And I think that's a very, very interesting observation, and we will want again to see more events to see if this works. Now, if this is true, if it is a off-axis GRB type of afterglow, and we know there was a GRB there, and the analysis of that GRB data also is consistent with viewing something with an angle of about 30 degrees. So this is all, the big picture is consistent with each other. If this is true, what we would expect for the radio emission. So in the case of the radio emission, the delay was even larger in the time it took for emission to be detectable from the system. I think something like 2 or 3 weeks, if I remember correctly. And after that, we had the system brightening for months, and until now it's starting to show a band in its light curve. And this is also consistent with the same idea, and it will be interesting as well to see more observations of the same system, but also more observations of other systems, hopefully that will have different inclination angles and so on, so that we can show that we are still being consistent. Okay, so now we already explored the R process nucleosynthesis component. We explored the jet component, so I think we covered the source itself. Now, the next thing we can do, and we can only do this well because we were able to identify the exact source, we now can look at its environment. We can look at the host galaxy and try to ask the question, is that host galaxy special, or is it a normal vanilla galaxy? So to first order, in the image that I showed of the galaxy early on, there's nothing really spectacular about that galaxy. It's an elliptical galaxy, and the analysis of it seemed to indicate that it's just a typical galaxy that could host a gamma ray burst. It's all very consistent. But looking in more detail and subtracting the smooth component of the light of the galaxy, you can see that there is a structure remaining that has like a ring type of shape. And that structure is characteristic from what we see when a galaxy suffers a merger. So at this point, I'm talking about a merger between two galaxies, one large galaxy, the host, and a smaller galaxy that doesn't disrupt it completely because it's small, say 10% of the total, but it's enough to cause this dynamical disruption of the environment of the galaxy. And that has been hypothesized as one of the possible mechanisms to aid in the evolution of the binary systems that would otherwise be in an orbit that would take too long to decay into an orbit that would decay in a time scale that we can observe. And that has a direct impact on the rates that we expect for the events. Again, with one event, we cannot tell if this is a really a mechanism in play, and there are lots of arguments for and against. But it's again another place where hopefully with more events coming in the next next year or so, we will start to make a sample of these events and their hosts and try to study if there are correlations between their properties or not. Okay, so now we get to my favorite topic. So in addition to understanding all of these great astrophysics, we also can attack now the problem of cosmology. The idea is that, that I illustrated here in this cartoon is that when a merger happens, we know that our colleagues in LIGO and Virgo can hear the gravitational waves from it. And we know now that we are able to detect the optical counterparts. So we can combine distance information that comes from the gravitational wave signal with redshift information that comes from identifying the source. And build the distance, by the distance redshift relation, we can tell how fast the universe is expanding, so measure the Hubble parameter that way. And this idea has been proposed in the 80s, so it is around for a long time. But for the first time, we were able to put it in practice. And this is particularly interesting right now because the other traditional methods of measuring the Hubble parameter are in conflict with each other. These results are showing tension of about 3 sigma at the moment and growing each time that those measurements improve. So having an independent new method to do this, the measurement of the cosmic expansion, it's fantastic. And we didn't know if we would be able to do it, but it looks like from what we can see here that yes, we can do it, even though in this case it's only one event, so the error bars are too large, so we cannot tell which of the other traditional methods is the right one. But it's a work in progress, and with more events, we'll get there. And you may ask, how quickly are we going to get there? And I'm prepared for the question. So yeah, that's another one that comes up often. So what I'm showing here is on the top panel, it's number of events expected as a function of time in years. And to calculate this, I need 2 pieces of information. One is the astrophysical rate of the events. And the second is what is astrophysical rate density, right? So number per unit volume per unit time. And the second number that I need is the volume out to which LIGO will be able to see something. So I took from their reports what is their expectation for the evolution of their sensitivity over time, and the yellow bar, the yellow band corresponds to uncertainties on the rates, astrophysical rates measured. So if you just look at the top there, that's like around 2023, we will be in close to 100 events. And I stopped the plot at that point there because that's like about the lifetime of a graduate student. I felt that that was the right time scale. On the bottom part, because I'm interested in this H-naught business, it's just a scaling with the square root of n, and I have some of my colleagues have done more detailed work in doing this measurement. I'm just estimating here, just square root of n. And to get to 2% uncertainty on this parameter, which would be sufficient to arbitrate between the 2 current best measurements, it would take about that amount of time. So I think that this is spectacular for any of us who have the privilege to be active in this day and age. It's really the future is bright. All right, so I'm summarizing already. So GW170817, of all of the gravitational wave events that LIGO has detected, is by far the most spectacular. And the reason for that, I hope I could convey here, is the wealth of science that we were able to do with this one event is, I think, unprecedented. We confirmed the hypothesis of this new class of astronomical transients, the kilonova. We were able to do this first time, this cosmological measurement, and so on and so forth. I think it's absolutely great. And now we are in great shape to do more of it and actually get to the point of doing precision measurements even with these events. And thank you very much.
We have time for a few questions. Yes.
You talk about measuring the Hubble constant. You can do this independently. Is it too ambitious to think that you can measure variations of the Hubble constant and determine the acceleration of the universe if you're able to go deep enough into space and have enough measurements? Would that be a reasonable thing to expect or hope for?
That will be more difficult because of the range out to which we get the events. But the idea is that next generation of these gravitational wave detectors will be able to see further out, and then eventually, I'm pretty sure that eventually we'll get there. But it's not in that time scale. That time scale, I think, the best we can expect is the H0 measurement.
I mean, a follow-up would be the type 1A supernovae that we're seeing, and I just wondered if you could use that as an independent candlestick. But
yeah, so the idea is that we would be able to check the lower redshift anchor of that Hubble diagram that is done with supernova.
So I thought I should call something out on behalf of my ex-student, Darren White, who was a PhD student at the University of Sheffield. And in 2010, he basically on his own, with a little bit of help from me and Vic Dillon, put together this list of galaxies called GWGC. And it's not really astronomy. We couldn't get it published in an astronomy journal because it was a mashup of existing astronomical catalogs. We got it published in Classical and Quantum Gravity. It may be the only galaxy catalog list they've ever published. And it ended up getting 43 citations for being the catalog that was used to point the guns at the optical galaxies in the field. And so Darren, 8 years after his PhD work, has now basically got the credit for giving people the data they needed to find this thing before it faded. So I thought it was a nice story for any PhD students here. The credit is his, not mine. My name's Ed Daub, but that doesn't matter. And thank you for giving me a chance to tell that story on behalf of students everywhere who think their PhD work might never be noticed, because his was. Thank you.
So on that beautiful note, let's thank Marcelle again for a beautiful talk and all the other speakers.